Okay, let's continue. This is the second video. So now we've got the diagram shows an unlabeled voltaic cell. That means, as you know, it's going to give out energy. Now we have to figure out which one of the lead or the nickel is the most reactive. And we come down to here. Oops, I'm writing on something wrong. I'm not writing on my tracker pad. Okay, here we go. Excuse me. Right, here we go. Right, so there's nickel and there's lead. Let's move this up a bit. All right, so of these two, then nickel is the most reactive. Why? Because it's got the more negative electropotential. So that means that's the one that will give off electrons, if you like. Give off doesn't sound very good, does it? But that was the one that will release the electrons because it has a greater tendency to form the negative ion. So this one's going to be nickel. And this is going to be the lead. And electrons are going to go that way, from the more negative one to the more positive one. Okay. This is obviously going to be nickel ions, nickel 2+ ions. And it doesn't say it, but as you know, the concentration has got to be 1 mole per decimeter cubed. And this one, what's this? This is lead ions. And the concentration of which must be 1 mole per decimeter cubed. Yeah, and it's only worth 1 mark, so that's not much good. Calculate the cell potential. Now, this will be said earlier, E cell is equal to E electrode minus E electrodes. Okay, and they're both in the standard states. Standard conditions, I should say. All right, now, which one is this? Well, this is the more positive. And this one is the more negative. Okay, so that gives us the more positive is, I can't see, 0.13 minus 0.13, minus 0.13, minus 0.26, which looks like plus 0.13 volts. There you go, piece of cake. No reason you should get any of those wrong, ever. Okay, where's next? Now we've got to do something similar, which we did before. Here we are, paste there. Let's move this over. Okay, wonderful. Calculate the standard free energy, change delta G kilojoules for the cell using 1 and 2 of the data booklet. Right, now I'm going to use this one. Delta G equals minus NF E cell. Okay, so that gives me, let me use a different pen, minus E. How many electrons are involved in the transfer here? Right, they're both 2, aren't they? So the nickel is going to lose 2, and the lead is going to gain 2, so that means N is 2 times Faraday's constant, 96,500, times E cell, which is 0.13 volts, and if we work that out, we get, where on earth is my calculator? It is 2 times 96,500 times 0.13, and I get 25,090. So I get 25,090 joules per mole, or 25.1 kilojoules per mole. Okay, and because it's negative, it's a spontaneous reaction. All right, so this is spontaneous. Why? Well, 2 reasons. Delta G is negative and E cell is positive. Both of these things mean it's spontaneous. If you look at this, because if E cell is positive, delta G must be negative, mustn't it? All right, because there's a negative there. I hope that makes sense. Let's have a look. What's next? All right. Now suggest the metal that could replace nickel in a new half cell and reverse the electron flow. Okay, interesting. So I don't know the answer. So let's have a look. So nickel is 0.26, and we want the other thing to be more reactive than nickel. So anything with an E electrode less than minus 0.26 volts. Okay. Now, I'm not even going to bother looking it up. Let's have a look. So to reverse the electron flow. Oh, hold on. Have I got that the right way around? Maybe I haven't. We've got to replace the nickel. Oh dear, I have totally got that the wrong way around. I hope you follow me why I've got that the wrong way around. Okay, because I thought we could replace nickel and we can get the electron flow to go the other way. But this one suggests a metal that could replace nickel. So the metal that's got to replace it has got to be more positive than this. More positive than the lead. So it's more positive than 0.13 volts minus 0.13. Because if that's the case, then the lead becomes the more negative and electrons would go that way, wouldn't they? That would reverse the electron flow. So a typical metal there is silver. We could use silver, the silver system. Okay, silver plus silver system. You could use that, or you could use copper, I'd imagine, yeah. Copper 2 plus, copper system. You could use that. All right, now silver, I've got a feeling it's 0.8 volts. Copper, I've got a feeling it's 0.34 volts, both of which are more positive than that. Okay, so there's your answer there. Let's have a look now. We're coming up to the end, guys, so don't worry. All right, if you're still with me, well done. Okay, make this a tiny bit bigger. Move it over there. Try and move it under there. And there we go. Describe the bonding in metals. Right, now I'm going to cheat here. What am I going to say? I'm going to say, where are we? Oops, daisy. Let's get that smaller. Describe the bonding in metals. Well, I'm trying to look for the answers here because I want to do something. I want it to be quite nice. Here we go. This is what the answer scheme says. All right. It says electrostatic attraction. Yeah, I guess so. I wouldn't have started off this. Electrostatic attraction. Certainly is that, isn't it? Between the lattice of positive ions. Actually, this isn't a bad one. Positive ions, or we could say cations, and the sea of delocalized electrons. All right, there you go. Okay, yeah, there you go. That's not a bad answer, actually. I would agree with that. All right, now where are the points? Number 1 for saying electrostatic, and then the second mark is for everything else. Okay, all of that is worth 1 mark, but you've got to get the 2 marks there. That's a perfect answer, actually, for what metallic bonding is. Nickel alloys are often used in aircraft gas turbines. Turbines suggest the physical property altered by the addition of a metal to another metal to nickel. In other words, what does alloying do? Now I'm going to read these out straight from the answers as well. Let me get a black pen. I haven't used black for a while. It changes the malleability. Makes them less malleable. Malleability. Increases the tensile strength. Tensile strength goes up. They're stronger. Obviously, I never thought of this, but it's obvious, really. It will change the density, won't it? Could change the conductivity. All right. Oh, melting point. It will lower the melting point, won't it? Because it's impure now. So it's going to lower melting points. What else have we got? And a weird one that no one would ever thought of, the thermal expansion rate. All right, which one would I have picked there? Malleability for sure. Strength, yeah, I would have picked that. Density, not obvious, but I guess that's okay. Conduction, I wouldn't have thought about it, but it's obvious. Melting point is also obvious. And thermal expansion, I wouldn't have thought of that, but there you go. Okay, all right, hold on. Okay, let's continue. There's only a few more to go. Which graph? These aren't equilibria. These are ones just I thought were kind of nice pictures, nice graphs, nice questions. Which graph represents the relationship between rate constant and temperature in Kelvin? I obviously the rate constant is going to increase with temperature. Okay, because obviously reactions get faster as you heat them up. So, well, it's not going to be zero. Well, I don't know. Actually, it might be. I'd say there, as the temperature increases, the rate constant increases. Is it going to be linear? Well, I don't know. If you could answer me that, do me a favour. I don't know. Is it linear? It's obviously one of these two because the rate constant will increase. But is it linear or is it an exponential? I've got a feeling it's an exponential because of Arrhenius. I'm going to guess that. But you know what? If you've got a problem with that, please ask me. I love arguments, you know that. All right. So now, what's the correct when the temperature increases in the reaction at equilibrium? What's correct? If you increase the temperature, as you can see, forward reaction is endothermic, so the equilibrium is going to shift that way. So it shifts right, one of those two. Equilibrium constant. Right, if you're increasing the temperature, that's the only condition where Kc it changes. Okay, and in this case, since the forward reaction is endothermic, you get more product. So product divided by reactants is going to get bigger. So this is going to increase. So the answer is that one, D. Okay. All right, so we're good there, I hope. Next one. Which statement is correct for a spontaneous reaction? Well, we all know that that's going to be negative. Kc, well, as I said, it's products. It's basically the concentration of products divided by concentration of reactants. So if you want it to go forward, you want this number to be bigger than this number. Okay, this number's got to be bigger, and this is smaller. So if that's the case, Kc is greater than 1, isn't it? So Kc is greater than 1. So there you go. There you go. Now see that that shouldn't be confusing. What is correct with iron is a stronger reducing agent than silver. All right. In other words, it's going to get rid of its electrons. It's going to get oxidized. So the electron's going to go like that. So I've already got one of these answers, haven't I? Electron is right to left. This is right. This is left. So right to left, yes. No. No. Right to left. The negative electrode is going to be the iron, isn't it? So it's got to be that one because it's the one supplying the electrons. And there you go, A. All right. If I get any of these wrong, please tell me. All right, but I'm pretty sure I haven't got any wrong. Which conditions deposit the greatest mass of copper when solutions containing copper 2 ions are electrolyzed for 10 minutes? All right, now where are we? To deposit a copper ion, you need 2 electrons, and to deposit a copper 1 ion, you need 1 electron. So it's easier to get rid of these. All right. So if for the same number of electrons you get more copper 1 deposited, so we're going to look at it's one of these two, isn't it? All right. And obviously, if the current is higher, you get more electrons flowing. So it must be D there. All right. And I think this is our last one. Which statement is correct when a zinc spoon is electroplated with silver? Okay. Now, I'm going to have to draw this because I forget these things. But now we're looking at an electrolytic cell. And in this case, I remember what we're plating. A spoon. There's the spoon. Okay, this, the anode, must be the metal we're plating with. So this is silver. And this is our spoon, and the spoon must be made the cathode because you want the silver ions, Ag2, Ag plus, to go onto them. All right, so let's see which one's right. The cathode negative electrode is made of silver. No, that's not right. It's the anode that's made of silver. The anode is the zinc spoon. No, the anode is the silver. The anode is made of silver. Yes, that looks good. The electrolyte is zinc sulfate solution. Oh, that's going to try and trick you, isn't it? Now, the electrolyte can't be zinc. It's got to be a silver salt. Okay, and not only that, it's got to be a soluble silver salt. So I'd always pick silver nitrate for that because I know all nitrates are soluble. So that one's wrong, and therefore the answer is C. Right, now let me get this posted right away.